Good morning and welcome to today's webinar, Modernizing 3D Sand Core Production with Inorganic Binder. Before we begin, I have a couple of short housekeeping items. Today's webinar will be recorded and made available to today's attendees, and you will receive an email with a link to the recording in a few days. Second, our presenters Andy Nagy and Amin Sergini will be answering questions at the end of the session. To ask a question, click on Q&A on your Zoom dashboard. A window will pop up for you to type in your questions. You can type in a question at any time during the webinar. Thank you all for joining us today. Now let me introduce our speakers. Andy Nagy joined X1 as Managing Director in December 2019. As the Vice President Printing Systems of X1, he oversees the development and operations of all X1 binder jet 3D printing systems, including both sand and metal machines. Amin Sergini currently works for HA, a well-known supplier of chemical products for foundries. For many years, he was responsible for the marketing and further development of the cold box products. Since the beginning of 2013, he has taken over the role as Vice President, Sales and Marketing, which comprises the sales activities of the international HA group. For that, I'll hand it over to you, Andy.
Thank you very much. Hello, everybody. Let's have a quick look at the agenda. I would like to provide you a quick introduction about X1 and the core technologies we're offering. I will then give you an overview of the 3D binder jet printers and processes that we are offering for sand production before Hytenes Albertus will give you an outlook into the future of inorganic binder systems. We will then spend a good set of time to review the workflow of the inorganic printing process, and we'll wrap up the session with an outlook to the sand 3D printing roadmap. I will start the introduction of X1 and its core technology. X1 is the global leader in binder jet 3D printing for more than 20 years. Founded in 1995 as the 3D division of Extrude Hone, it grew over the years to a company with more than 310 employees, with worldwide operation and production sites in the US, Germany, and Japan. In 2013, the company went IPO and is NASDAQ listed since, and was successfully growing over the years. Even during last year's pandemic, we were able to improve our revenue where other companies declined, which results in a recent significant rise of our share price. The core business of our company is in industrial-grade binder jet 3D printing systems and services for sand, metal, ceramic, and composites. The main benefit for our customers is the 3D printing capability for high-value parts in small, moderate, and large volumes. With our systems, we're serving industrial markets like foundry, automotive, aerospace, and all other markets where high-value parts are required. We're proud of our worldwide installations of far over 325 sand and metal 3D printers, which will be able to support also ceramic printing. As shown on the table, we delivered into countries in America where our company headquarters is located, as well as into Europe and Asia. We will be able to support all areas through our regional headquarters, as well as through the offices of our local distributors. X1 binder jetting is focusing on 4 primary application categories. The first is printing of complex 3D sand molds, cores for castings, substituting pattern making requirements. The second is direct 3D print of complex single alloy metal parts in higher volumes and a lot faster than other laser 3D printing technologies. Our 3D printers can also be used for direct ceramic parts printing, which is simplifying the production, for example, of silicon carbide parts. The fourth application is the 3D printing service of sacrificial water-soluble tools for vacuum and hydroforming compound parts. Let's focus now on the benefits of the 3D binder jet printing of the mold and core package for complex sand casting parts. The conventional process requires, after part and pattern design, the manufacturing of the cores and mold with the time-consuming and expensive multi-step manufacturing process of the pattern. This typically requires, after pattern manufacturing core shooting, the assembly of multiple cores before it gets assembled to the mold package for pouring. The digital process instead only requires the print of the mold package and provides therefore a very significant time reduction. Besides the significant time reduction, there are many other benefits of this transformation. There are a lot of savings offered by the elimination of patterns, molds, and their cost-intense physical storage. In addition to the saving of labor will be the yield improvement, having no need for the yield-critical assembly step of multi-core assemblies, as all cores can be printed in one single piece. Design changes will be able to instantly drop into production just by CAD file modification, and the direct 3D print of CAD designs will enable exceptional design freedom, allowing to ignore any former pattern making constraints and design rules. We at X1 US offer to our customers full support for sand casting with our 3D printing technology and our foundry engineering experience. The goal would be to offer a successful casting in one iteration only, what we call one cast. Especially those customers that would like to explore this new technology will be able to benefit from our services. Our 360-degree support includes not just 3D sand core and mold printing, qualification and inspection, but could also include 3D part design, engineering and finite element modeling services, as well as foundry sourcing and training how to optimize digital mold package design. X1 was the first company offering 3D binder jet printers for sand in early 2000. Our machine capabilities developed over the last 20 years from the introduction of the technology for low volume requirements. And in the last 10 years, we introduced 3 new platforms for constantly growing volume applications, up to the automotive inorganic core manufacturing and production with our former X-Serial printer, which we successfully launched at 2 large automotive car suppliers. All this experience went into the most recent platform launched in 2019, the S-Max Pro, a modular printer ready for the mature production era that is in front of us. Let's have a look at the available production solutions for binder jet sand printing. The X1 Sand 3D printer portfolio starts with the S-Print on the left side that is available since 2005. With the 160-liter removable build box, it is supporting all binder systems and is most suitable for academia-rapid prototyping and low-volume production customers. The S-Max, with the large job box of 1.8 by 1 by 0.7 meter, offers already a quite decent build rate up to 100 liter per hour and a double job box option to be able to print the next job while the first job is getting unpacked. It is a good entry system for furan and cold hardening phenol binder applications. The new S-Max Pro comes with the same large job box and double job box option, but it is offering in addition a high build rate of 125 liter per hour for furan and cold hardening phenol, as it comes with an enhanced print head and recoater. It supports with a removable job box of its box-in-box configuration with the ability to cure the job in a microwave for inorganic and hot hardening phenol applications. The most exciting special of the S-Max Pro, which is making it ready for Smart Foundry and Industry 4.0, is the quality control system enabled by Siemens Industrial Control Technology and its IoT capabilities. In 2019, X1 started a collaboration with Siemens to get the machine ready for smart factory requirements. With the introduction of Siemens Industrial Control Technology into our S-Max Pro, we are able to offer the Siemens Industry 4.0 ecosystem with the following three capabilities to our customers. Via the Siemens MindSphere cloud-based service and our X1 Scout app, we offer remote process control and any smart device or desktop. Process quality assurance is supported by Siemens Industrial Edge device and new developed apps to control the build process via camera inspection of the build area and performance analysis using artificial intelligence algorithms. The Siemens PM quality software stores historic job data long-term into an SQL database for job-to-job data analysis and statistic process optimization. With these capabilities, the system is offering a superb quality system and making it ready for true volume production. We are offering 4 different binder systems to support different metal and casting applications. More than 80% of the business runs with the organic Furan binder. The high achievable core strength of Furan makes it suitable for applications from aluminum up to steel. As the parts are curing right after the print, they can get harvested from the job box without an additional curing step. The organic hot and cold hardening phenol binder systems can offer even higher strengths and sharper contours of final parts. The cold hardening phenol process requires an oven for individual parts curing, but at the hot hardening phenol process, the whole job box gets cured in a microwave. Then the environmentally most friendly binder system is the inorganic system, which is requiring a microwave for job box curing as well. But even there is this extra step, the demand for it is constantly growing. The most common sand used in the inorganic process is similar to the Furan process, the less costly silica sand. The reason for the foundry industry to move towards inorganic 3D binder print and inorganic 3D printing are the irresistible benefits. The major advantage is the low emission for printing and casting. The nature of the inorganic binder is its negligible organic content and therefore the lack of gas emission during printing, and even more important during casting. Core vent designs that remove trapped gas during casting are much less critical if there is no organic content in the binder to burn and exhaust, which will finally lead to higher yield. The inorganic binder system chemicals are environmentally friendly and easy to handle and store, and clearly leading the way towards the green foundry. Last but not least, the inorganic 3D printing process offers significant cost reduction that will get further explored during this webinar. The major advantage of using a low-emission inorganic binder for the 3D printing of sand cores is the improved air quality in the foundry and the improved yield of the castings because much fewer exhaust gases are generated. Core vents that remove trapped gas during casting are no longer needed because no such gas is created. There is almost no organic content in the binder to burn or vent. This will help to avoid gas bubbles in the casting and is therefore leading to higher yield, as I mentioned. The shown graph compares the loss of ignition of a 3D print with Furan and inorganic binders. The LOI percentage is kind of a reference how much binder was used and is referring to the surface underneath the curves in the graph. As you can see, the pure silicon sand by itself is contributing with about 0.2 to 0.3% of LOI. The inorganic binder is adding just very little to the final LOI, but at Furan, the combustion of the organic binder is creating significant more gas emission. Let me now hand over to Anime to give us his insights.
Thank you, Andy. So welcome to the part of Hüttenes Albertus in this webinar. You know us probably as HA or HA Group. We are a family-owned company with a very long tradition in manufacturing products for mold and core manufacturing. And our company's success story began more than 100 years ago in Hanover, in Germany, as early as 1905. In 1970, a joint venture was formed from the Albertuswerke in Hanover and Gebrüder Hüttenes in Düsseldorf, both giving origin to the two-letter H and A. And in Germany, Germany is still the headquarters of the company and main base for R&D as well as services. It's also the largest market for HA in terms of sales and employees with 540 people. So we have a dense network in Europe as well. Here we employ 1,200 people, and worldwide we have a total of 1,800 employees active in 35 countries. So the HA Group is everywhere in the world where foundry industry is significant. We run 26 manufacturing plants worldwide, and our focus is on innovation, sustainability, and process efficiency. With 150 chemists worldwide and a central research and application facility in Germany, we feel ourselves well positioned for the future, a sustainable future. Sustainability is leading our activities in R&D and production. We all know the industrial processes have an impact on our natural environment. As a part always at our customer sites, the topic of sustainability is also a focus for us. Foundries are challenged in these days by more and more stringent environmental and safety regulations. Particularly problematic is evaporation and cracking products released during casting and subsequent cooling of the molded parts. These parts are mainly made from resin-bound sand. Emissions and the related odors are released from the sand molding during casting and during manufacturing process. The generally used organic binders have, of course, been improved over the years, but there are still problems that need to be tackled. This means that alternative binder systems are increasingly in demand. Here, inorganics and inorganic binders are coming more and more into focus. This lower emission, fewer odor during production and casting especially of aluminum. Since January 1st, 2021, that means this year, there is a new stricter limit value for emissions in Europe. The total C emission allowed is below 150 milligram per cubic meter, and a target value of lower than 50 milligram per cubic meter is aimed in the future. And the target value the target value applies already today to production expansion and new plant projects. In respect to USA, we have no precise knowledge of existing limits. However, we expect stricter targets in the near future by the newly elected government. More sustainable binders will be required. And you know, sustainability is also playing a more and more decisive role in the automotive supply chain. Coming now to the binder systems for additive manufacturing. On this slide, we see a summary of existing binders for additive manufacturing, as also explained from Andy before. And the major process in use is organic with more than 90%. This for sure include the furanic resin, phenolic, and the others. And the new and fast rising additive manufacturing processes with inorganic binders. If we look at the start of additive manufacturing using sand, so we remember the laser printing process. A coated sand or pre-coated sand was partially heated for curing. And the binder jetting started at the end of the last century, and straight away furan resin turned out to be very suitable for this application. The following modifications cemented the fitness of this binder. Also, other phenolic processes have made their way into 3D printing, but furan remained the dominant organic binder for this application. The rigidness of the process and suitability for all metals is one of the advantage of Furan process. The further development of the process in terms of environmental aspects is one of the major efforts in the R&D at HA. Following the elimination of resorcinol in the resin RPT2, bisphenol A has also been successfully removed from the formulation in RPT3. Looking at the inorganic side, we can say since the inorganic process was introduced in the production of aluminum castings in automotive foundries, the demand for the use of inorganics in additive manufacturing also increased over the time. Various stages of development have made IOB 3D printing suitable for volume production. Already a well-known OEM from Germany has been using this process for more than 4 years now for the production of complex cylinder head parts. A large-scale production is about to start using the binder jetting process, and further projects are in the planning or implementation phase. Certainly, the biggest advantage of inorganics is the almost zero emission during the molding process as well as after casting. In the next step, we will see a comparison between the two additive manufacturing processes in terms of performance and environmental impact. So this slide shows the main aspects when evaluating 3D printing binders. The upper part are showing positive performance, and the lower parts describe the intensity of deficiency of the different binders. So if we look on the emission, as already mentioned, the strength of inorganic lies in the fact that they are almost emission-free during the production of moldings as well as after casting. In the Furan process, emissions are present during the production of the molded parts as well as during finishing. CO2 and BTX emissions are also expected during casting. In the respect, further steps toward better environmental performance have already been taken with the RPT2 and RPT3, and further development are currently in the pipeline. Going to the production speed, Furan's key benefits is the speed of the printing process, the favorable for viscosity and reactivity of the system, as well as the optimal drop formation and at surrounding temperature have a positive influence on this aspect. In the inorganic process, tempering of the surface layer is necessary to stimulate reactivity when using silicate binders. Recoating in this case takes place at a slower rate than in the Furan process, which explains partly the slower printing speed. On the curing side, so the Furan process, the high reactivity leads to a fast self-curing and allow further handling without thermal post-curing. About 80% of the strength level is reached after 4 hours, and therefore post-treatment is not necessary. In the case of inorganics, the current state of the art requires thermal post-treatment, and this is done by post-drying in the microwave, as explained through Andy, prior to the removal from the job box. This intermediate step also influences the process time of the inorganics. Comparing finishing, so during the self-curing of the Furan binder, a gas push occurs at the interface zone of the curing, and it leads to further unintended reaction of neighboring activated molding material. This manifests itself in unfavorable mold fidelity, which can only be corrected with the appropriate care by the finishing. In the case of inorganics, the molding material is not pre-coated with a liquid, therefore dry. This dry molding material in combination with the reduced interface zone reaction leads to a clear boundary and therefore to a better finish. If we compare the storage stability, Furan moldings have a longer storage stability regardless of ambient conditions. With inorganics, the problem of moisture absorption from ambient air and deterioration of strengths requires greater care during storage and also transportation. With this slide, we show in the yellow market part the actual improvement made of both Furan as well as inorganic in comparison to the former one. So you can see the change compared to the initial stage. In recent years, R&D has done a lot to remedy the negative issues of the systems, especially in regard to inorganics. In details, these are from emission. As mentioned before, we have noticeably improved the environmental aspects of the Furan binder by eliminating both resorcinol and bisphenol A in 2 steps. Therefore, 1 step up in the ranking. On speed and curing, so the use of new additives to the molding material lead to significant improvement in terms of strength and flowability. The initial strengths are then increased in the case of inorganic. As to casting temperature, so in inorganics, we already found a way to also cast ferrous metal. Previously, this process was reserved for aluminum casting, and the thermal stability and especially the shakeout is now much improved. For the storage and the storage stability, the new additives allows in inorganics the increased moisture resistance. This allows improved storage for complex thin-walled moldings, and handling is also better. Last but not least, we would like to share with you the outlook and ongoing development for binders for 3D printing from our side. So HA is convinced that 3D printing technology will find its way relatively quickly into both job foundries as well as in series productions. That's why we have a multinational team engaged in R&D to further develop new solutions and tweak existing products. If we look on the molding materials, so we are convinced that some properties will be improved by the right choice of the molding material. Preconditioning of molding material is also a promising way to make this manufacturing process a greater success. Thermal behavior, decomposition, and sand reclamation are definitely parameters that are influenced by the molding material. This is a field of exploration for HA, and we do see potential on it. As to organic, so for Furan, our focus remains in the area of increasing printing efficiency and finishing, but above all, the improvement of binder classification. Our ambition is to present a label-free resin in the next future. As to inorganics, the inorganic sector has been on the market for a relatively short time. Nevertheless, a lot has been done in this field. We are confident to significantly improve the issue of initial strengths and flowability through new developments. The extension to ferrous materials is in preparation, and the moisture resistance on the usage of water coatings is also a topic we are currently dealing with and where we want to present solution soon. So with this information, I hope to have made the word of binder for 3D printing a little more accessible to you and have shared the ambitious goal of HA together with X1. So thank you for your attention, and now I give back to Andy for the next section.
Thank you, Anime, for sharing this information with us. I will now continue to walk you through the workflow of the inorganic printing process. But before we jump into it, I would like to introduce you quickly with this one slide to the current baseline Furan process and its workflow to be able to better explain afterwards the differences of the inorganic process. The Furan process starts with digital job preparation when the parts are getting arranged in a virtual job box and finally sliced into bitmaps for the printing of the individual print layers. This data gets conveyed into the 3D printer where all the parts are getting printed in a job box layer by layer. And this is where the processes are still the same, but then for the following process steps, there will be the difference. So after printing, the job box of the Furan printing process conveys from the printer to the descending station, while a new job box can already enter from the other side to start the next print job right away. Only short time later, the unpacking of the parts in the descending station can start. The loose unprinted sand gets pushed into the collection bins on each side of the box and will get vacuum transferred into a separator bin and recycle bin. The the parts are instantly ready for final finishing. Now, the three biggest advantages of this process are the single-step printing without additional curing process and the good strengths for high-temperature casting applications, as already mentioned from Anneme's side. But the shortcomings are the fairly intense labor requirements for finishing, the loss of ignition of the organic binders that requires to be managed to control gas emissions during pouring, and the potentially regulatory constraints due to the use of fluorophore alcohol in the binder. Let's now compare it with the inorganic process and its workflow. As you already can see, there are quite some additional ancillary equipments required. The differences to the Furan process are the interchangeable Boxinbox job box and the conveyance to move it to the microwave for curing the parts. After curing, the box gets transferred to the auto descending station where unpacking of the parts can start. The sand will automatically drop out of the box through openings at the bottom of the box, and this will allow to descend the box about 95% faster than what it would take for normal manual unpacking. However, to be able to make use of this time saving, it is most practical to print just one layer of parts in a box to avoid that parts would drop on top of each other. Another benefit of the inorganic workflow is the much easier and quicker finishing step. As there are less residuals on the part surface, the sand will come off much easier and faster. Let's deep dive and review each step of this workflow. At the beginning of a print job, we have to prepare the job data. The job preparation typically gets done on an offline PC with a third-party CAD software-like tool, such as Autodesk NetFab, Materialize Magics, or Siemens NX. Other third-party tools that offer a CLI interface could also get used, but would require qualification testing. With this job preparation tools, the part STL file are getting loaded, eventually duplicated and arranged within the job box as they should get printed later in the job. According to the binder application specific rules, support structures might get added. Such support structures may help, in example, if very fragile and thin parts should get unpacked later from the job box without breaking them. After arrangement of the job box, the data gets handed via CLA interface over to XPrep, an X1 proprietary tool to prepare the print data for the job by slicing the job into hundreds or thousands of bitmap files for each print layer. XPrep then provides the print data comprising all layer-specific bitmap image data and the job-related machine control data to the 3D printer, and the print job can get started. For the introduction of the binder jet print process with the S-Max Pro, I would like to invite you to watch a video that will illustrate nicely the repetition of the relevant sand bed recoating and printing steps. Yeah, the three benefits of the inorganic printing process are, again, the low emission during printing, the environmental friendly inorganic consumables, which are making handling and storage much safer. And we will get also a slight labor cost reduction as the recoater cleaning cycles will be reduced compared to the organic processes. The main enabler for printing inorganic binder with the S-Max Pro is the so-called Boxinbox system. We're offering an interchangeable chop box to support the offline microwave curing, while the printer can continue after a quick box exchange with the next print job in parallel. Besides this performance improvement, the integrated base plate perforation will support fast auto-descending, providing further savings. Due to the auto-descending capability, the reduced job height of 400 millimeter is not becoming a performance issue. As with auto-descending, a one-layer part print job will improve productivity by shortening the line index times. With this capability, the Boxinbox system can support all binder systems, but it will provide certainly the most benefit for the inorganic and hot hardening phenol process. With this layout illustration, I would like to give you an overview how the interchangeable chop box conveyance setup could look like. Once a job gets finished, the chop box will move out of the printer, carried by the shuttle F, and it will get conveyed to the microwave via the roller conveyor G and the transfer belt I. In parallel, the next empty chop box waiting on the transfer station D will shift into the shuttle F to get shuttled into the machine to start the next print job. After microwave curing, the chop box will transfer over to the auto-descending station. Before we talk about this station, I would like to spend a moment on the microwave process step. The microwave, developed by X1, has just one duty. It helps to evaporate the water component of the binder and therefore aiming to get to an operation temperature of about 120 degrees Celsius. We're heating the whole chop box at a time, including the support sand, in a time of only about 30 to 40 minutes. This is significantly faster and much more efficient compared to an oven process, as the microwave is curing the cores from inside out. Besides of the longer heating cycle, the oven process bears the risk that the outside-in heating introduction would cause water to get trapped if the core boundaries would cure prior to all evaporation of the water that's still inside. This process works very well with silica sand. With the automated descending station, we are offering an automation technology that is significantly increasing the overall equipment efficiency and saving cost. The chop box will enter the descending module via the transport module. The flowability of the unused sand and the perforated floor integrated into the chop box allow the unused sand to drain in minimal time. The automation of this task will also help to improve the yield during descending. A screw conveyor then transports the unused sand directly to the recycling container for instant reuse with the next print jobs. Please watch with me the movie that I'm going to start now, and you will see how fast and nice the sand drains through the holes and empties the box about 95% faster than with a manual desanding procedure. So it reduces really the time of a partially filled box of 90 minutes down to just 3 to 5 minutes. So for unpacking of the cores, the bottom of the chop box will raise to the top for better ergonomic access. And additionally, air vacuum from the left and right funnel sides will reduce fine dust pollution. A future expansion with full automation can get achieved by adding robots to remove the cores fully automatically. Now we're coming to the finishing of the part. The inorganic printed parts typically have excellent surface quality with only few residual particles. The finishing is therefore much easier compared to a Furan part, as Anime already pointed out. For manual finishing, a soft brush improves the time, but it could be done as well solely by blowing with compressed air. And this opens the potential for full robot automation of the finishing process step. Finally, we're getting to the specifications of the final inorganic part. The bending strength gets adjusted prior to the print job by the printhead resolution settings and is typically in a range of 250 to 400 Newton per square centimeter. The hot bending strength is currently lower than at Furan, but very well suitable for aluminum alloys. X1 is already working with our partners to further improve this. Even it is challenging for a process with heat treatment, for curing the dimensional accuracy of the part is at plus minus 0.5 mm, dependent on size and geometry of the components. However, we have successfully demonstrated with our customers that these tolerances can get significantly improved in volume production. The inorganic parts are hygroscopic and finally even water soluble. It is critical to either use the parts soon after printing for the pour or control the environmental conditions during storage and transport. The strength drops with increasing humidity and therefore a relative humidity of 40% and temperature of 30 degrees Celsius should not be exceeded. For storage, it is also recommended to provide evenly balanced support, in example with foams, to avoid bending of fragile parts. For wider distance transport, it is recommended to enclose the parts in airtight plastic with desiccant bags to minimize the moisture content. You did get so far all workflow information of the inorganic 3D print process, and I would like to wrap up this webinar talking about the inorganic 3D printing roadmap. But before, I would like to quickly recap the benefits of the inorganic 3D printing, as you got now all the background to understand those claims. The major advantage is the low emission for printing and casting, as it will finally lead to higher yield and improved environmental condition in the foundry. It is supporting our way to green foundry, as the chemicals of the inorganic binder systems are environmentally friendly. And third, the inorganic 3D printing process offers significant cost reduction with the labor cost saving of the auto desanding, the minimal finishing requirements, and a reduced recoater cleaning effort. But another big saving potential comes with the potential for further automation. And I would like to stress this a bit with the last slide of this webinar. The process for transporting the box from the printer to the microwave and from the microwave to the auto descending station is already a first automation step, which saves a considerable amount of time. But as one automated descending station can serve up to 4 3D printers, and this is the same for the microwave, it is cost efficient to link together several binder jetting machines as shown with this illustration. But this is just the beginning. Ultimately, this process opens up the ability for full robot automated core handling. A robot can take on the task of unpacking the cores from the auto descending station and put them on a line conveyor to transfer it to the finishing station. The excellent surface quality with only few residual particles opens up the ability to do the finishing by a robot as well. And there are already 3D scan solutions in the market that are supported by a robot handling. And finally, a robot may place the cores into the mold or into the storage cart. The third roadmap item is the improvement of the thermal strengths of the binder system to support higher temperatures of other metal alloys. We hope we were able to provide you the information you expected from this webinar, but if you have further questions, we will be happy to answer them. Thank you very much for taking the time today with us.